Hello and welcome to NHP's webinar on Type 2 coordination for motor starting. My name is Ron Pryor. I'm a technical training leader for NHP Electrical Engineering Products. The goal for today's webinars is to cover the following key points. Why is Type 2 coordination required? The testing processes required. How these are applied for tables for IE3 Premium efficiency motors, and look at a real life operation on site. For a typical DOL starter, the minimum requirements of a motor starter are from AS NZS 3000. Short circuit protection is required, and the most common device now used is a circuit breaker, but fuses may also be an option. Motors are required to have overload and over temperature protection, and normally use an overload relay, which also provides overload protection for the cables. The contactor gives us functional control for starting and stopping the motor, and is normally selected based on AC3 duty. These are the three components normally associated with a DOL motor starter circuit. AS NZS 60947.4.1 is the standard for motor starters, and this defines the performance requirements for Type 1 and Type 2 coordination. With Type 1 coordination, it basically provides that the fault is interrupted safely without damage to other equipment or personnel, and the components, whether the contactor, overload or MCCB, are damaged, they could all be replaced prior to putting the motor starter back into service. Whereas with Type 2, the key points are safety as per Type 1. However, the starter shall be suitable for reuse without replacing components, and can be put back into service after the cause of the fault has been found and rectified. Welding of the contactor's contacts, provided the weld can be broken by a tool without deforming the contact set, is okay and accepted by the standards. So why do we have Type 2? Whilst the initial cost of a Type 2 combination will be slightly more than a Type 1, it is a cost of lost production. Should a short circuit fault occur at the site, it is a consideration for the end users. A Type 2 combination will allow for the motor starter to be returned to service quicker, as replacement of components is not required. The first component to be selected is the MCCB, with an ICU ICS value relevant to the prospective short circuit fault level. The motor starting curve is overlaid onto the MCB time current characteristics. This is done to ensure that the MCCB does not trip during start, with typical motors having 6 to 7 times full load current for a locked rotor value. With the use of IE3 Premium efficiency motors now in common use, they have an increased inrush current at start, which also has to be considered, we'll cover this later. It is common to only use MCCBs with magnetic only or instantaneous trip units. If the trip unit does have thermal or long time element, this should be set to maximum. The second component is a proposed contactor, which has to be matched to the let-through energy of the short circuit protective device with the fault withstand of the contactor. If the let-through energy of the MCCB is too high, welding or fusing of the contactor contacts will occur as a minimum. Once we have the best estimated selection of a contactor, the combination has to be tested for verification. Test panels are built with a maximum cable length of 2.4 meters per phase. This covers from the line connection from the test laboratory connection, interconnections and between components, and connections to the shorting link. The cables are of a cross-sectional area relative to the starter kilowatt rating. For testing of a starter combination, it is verified at two levels. The first is the R value, which varies based on the starter size and is a lower fault level, which would be a real-life incident and is in the region of the instantaneous tripping point of the circuit protective device. Two short circuit tests are performed in sequence. The O test is performed with both MCCB and contactor closed, and then the test circuit is energized. As there is a short circuit on the load side of the contactor, the MCCB opens to protect the circuit. Then the CO test is performed with MCCB closed and test circuit energized. The contactor is remotely closed onto the fault and the MCCB opens to protect the circuit. The R value, with the release of the 2015 standard update, Table 13 is maintained. However, Table 17 has been added to define the R testing fault levels for the starters. The R value for a starter up to 12 amps is 1 kA, whereas a starter with a between 500 to 800 amp starter has an R value test level of 30 kA. Table 17 is a harmonized table to provide commonality for IEC and North American market UL testing requirements. IQ is the test level for which the starter combination is tested to, being the nominated prospective fault for the table. The two short circuit tests are performed in sequence. As with the R sequence for O test, the MCCB opens to protect the circuit, and the CO test, the contactor closes, then the MCCB opens to protect the circuit. For a combination to be verified as type 2, it has to pass the 4 short circuit tests. Plus, each panel, following the completion of the O and CO sequences, is tested for its electrical properties. This is to ensure there is no damage to the breaker, contactor, housings or terminals, and there's no breakdown of the insulation, phase to phase or phase to earth. As said before, a contactor weld may occur, but to be confirmed as a pass, an additional test of 10 rapid switching on-off cycles at twice the starter rated current has to be completed. A Type 2 table is compiled from a number of tests. Not every kilowatt rating is required to be tested, but are compiled around frame breaks of the circuit breaker and contactors for a table which is in accordance with the standards. So normally you would test the circuit breaker with a higher trip rating with the smallest compatible contactor. and this may cover a number of starter ratings. Example would be for the 100 amp breaker with testing to a 72 amp contactor, you could utilize the 85 amp contactor without an issue. Or if you're testing with a 63 amp breaker and the 43 amp contactor, you could use a smaller trip unit being 50 amp with that same contactor. Whilst you can change trip ratings, you cannot change trip unit types. The MCCBs with thermal trip units have resistive elements, which adds to the total circuit impedance, which adds to reducing the peak let-through energy during opening, whereas an electronic unit does not. As the let-through energy and tripping times can vary, both trip unit variants have to be tested. We have tested the Terasaki MCCBs with Rockwell Brand's Sprechen Allen Bradley combinations. The tables compiled have been formatted for premium efficiency motors to prevent nuisance tripping during start. This is due to the high inrush peaks, which can be up to 22 times the full load current. The starter trip multiple is based on the magnetic tolerance band at maximum setting. The contactors are sized from the MCCB requirement and also selected to suit higher locked rotor currents, with premium efficiency motors seeing up to 9 times full load current. Type 2 coordination tables for sites with MEPS or IE2 motors are available if required for existing switchboards, as the MCC cells may have limited space. As you can see, there are a number of starter sizes impacted with some IE3 kilowatt motor ratings. So some frame brake sizes where for a 90 kilowatt on MEPS 2 motor you would utilize a 250 amp breaker frame, but with IE3 you would have to go to a 400 amp frame breaker, so the physical size is an issue, and this is occurring on a number of frame sizes of the breakers. New switchboards should be constructed based on IE3 Premium efficiency motors. Fuses as a short circuit protective device are now less utilised as MCCB technology in energy limitation has increased. Fuses can still offer a more compact solution, especially at 690 volts, as the fuses are I2T based, plus the instantaneous inrush of premium efficiency motors does not cause the same issues. Type 2 coordination for soft starters also exists. However, the testing for soft starter Type 2 coordination is from AS NZS 60947.4.2 and does have variations from the contactor starter testing. The weak point of a soft starter is the thyristors SCRs, so high-speed semiconductor protection fuses are needed to be used for short circuit protection. An MCCB or normal fuse will not open quick enough under a bolted short circuit fault condition to prevent damage to the thyristors. There's a number of requests for Type 2 coordination tables for VSDs, but these do not exist. Type 1 is not defined in any standards associated for variable speed drives. Offering feeder circuit type 2 with just an MCCB and contactor provides the same intent, reduced downtime on a fault. This is assuming the VSD self-protects under a short circuit or fault. To help understanding of what is involved in the testing, we have a couple of videos taken during testing for you to consider. First off, a 65 kA short circuit. And the shock wave of the short circuit opening actually caused the camera to move. The second unit was a contactor closing onto at a fault level of 3 kA. As this all happens in milliseconds, it doesn't really look too spectacular. But what you didn't see is, as the MCCB trips, arcing gases are vented, plus material is melted and vented also. So you can see with the arcing, both contactor and circuit breaker, and here material is being vented from both devices. Whilst the three-phase bolted short circuit fault is the least common, you have to consider the energy released as the circuit breaker and contactor interrupt the fault, giving off heat and pressure. The switchboard construction needs to consider this energy. Even though at low fault levels of our tests, the thermal release function is being triggered with the magnetics and opening time can be slower. This contactor is closing onto a short circuit value of 3 kA with a 100 amp MCCB, whereas this one here is a 250 amp MCCB tripping from a short circuit at 5 kA. So even at panel board level, the energy released as a breaker and contactor interrupt a fault with the heat and pressure can cause doors and escutcheons to be blown open if not properly secured. If we look at the MCCB and contactor, which passed in the first test video, there is sooting marks on both devices where arcing has been vented. These components are suitable for continuous service, but maintenance inspection of the MCC cell should be undertaken to ensure the vented gases and material have not caused insulation degradation elsewhere. The MCCB and contactor here have seen a short circuit fault, but when these starters are installed at a customer site, from the testing they can be placed back into service. However, it is wise to schedule a maintenance inspection during a plant maintenance shutdown period, as once on site, when a starter combination has been in service for a long period of time and there has been some MCCB trips and the contactor has been subject to some DOL starts, the performance can differ. With maintenance procedures and type 2 selected components, these will provide the end customer minimal downtime and minimal lost production in the event of a short circuit fault occurring. Plus, if you are replacing a motor, verify that the starter components are suitable for the new motor, especially if an IE3 motor is being installed. If you have further inquiries about Type 2 Co-Ordination, please contact your local NHP sales representative in conjunction with myself. This concludes today's webinar. Thank you for joining us for this webinar. I hope you have found it beneficial and helped in your understanding of Type 2 coordination.